We are now live. I'm just waiting for the YouTube page and then we can get started. We are now, whoops. Yes, we are live. Okay. Do you want to wait maybe a minute or so for more people to sort of come through?
Yes, sir.
Okay, we can do that. Okay, so we can get started if you like. All right, so good morning, good afternoon, I should say, everyone, and thank you so much for coming today. So my name is Aditya, and I'm the head of math and informatics at the Edinburgh University Young Scientific Researchers Association. And today we have an incredible talk for you. We have a very special speaker who's come to talk to us about quantum computing and its effect on cybersecurity. And our speaker is none other than Petros Walden. He is a lecturer at the School of Informatics at the University of Edinburgh. He holds a master's degree in mathematics from the University of Cambridge and a PhD in physics from Imperial College. He has around 50 publications to his name with topics in quantum computing, quantum cryptography, and the foundations of quantum theory. He's also on the management team of the EUYSRA Collaborative Computational Project Quantum Computing and of the Quantum Information in Scotland Network. He's also an investigator of the EUYSRA Quantum Computing and Simulation Hub and general chair for the International Conference on Practice and Theory of Public Key Cryptography. These words are a little hard to pronounce. So thank you so much for coming, Petros, and we look forward to hearing about your exciting work with quantum computing.
Thank you. Thanks for the introduction and for inviting me to give this talk. So let me first share my screen. Can you see the screen now? Yeah, well, I am.
There is about a 20-second delay for viewers, so they'll be able to see it a tiny bit afterward. But yes, we can see the screen.
Okay, great. So this talk is on quantum computing and its effect on cybersecurity. So it's more about the field and the effect on cybersecurity, and just a little bit specific on things that myself and my group are doing. But I thought that it's more important to place the whole field before saying details. So within an hour, that's plenty of material to go. Okay, so this talk is also for general university students, so I don't assume any knowledge on the field. So the structure is the following. I'll start with explain the unit of quantum information, the quantum version of a bit, the qubit. And then I'll go explaining how the quantum speed up conceptually it arises, and misspell a number of misconceptions. So basically clarify what it is possible and what is not possible with quantum computing, because it's very, for hyped topics like quantum computing, is very important to be precise. Then I'm going to say a little bit about quantum technologies and how it's no longer a theoretical concept and it's something that is happening now. And then I'll give the definition and landscape of the field of quantum cybersecurity, which is exactly the implications of quantum computing on the field of cybersecurity. And in that place, I'll also say a few more words on my research as well. Okay, so we'll start with the unit of quantum information. So what is a quantum bit? A quantum bit is a physical system that has two possible states, the same way that a bit is something that can take two values, and it doesn't matter whether a bit is a coin or whether a current passes or not, or a switch is turned off or on. is basically this is a unit of information. It's irrespective of its physical implementation. Now, similarly, a quantum bit is the same thing, but for a quantum system that has 2 states. So examples that are used are photons, the different polarizations or the different arrival times of photons, coherent light, electrons, nuclear spin, optical lattices, superconductors. So there are many different types of quantum bits and different types of quantum hardwares that are being developed. So unlike classical computation, which is very well developed and people don't speak about this because it's already established what is optimal, in the quantum case, different physical implementations have different advantages. So this is something that I'm not going to speak in this talk at all, but it's something to keep in mind. Okay, so what is a bit is something that can take 2 values, 0 or 1. Now, quantum bit is more strange because in a very loose sense, I mean, it's not that it's simultaneously 0 and 1. We're going to see that this is one of the misconceptions, but in certain circumstances, it behaves as being simultaneously 0 and 1, not 0 or 1, being both 0 and 1. That's it appears that it behaves in this way. So this is a loose analogy, but it's important to know. And because it can be both 0 and 1, it can also be different degrees of being 0 and 1. So it's something continuous in a sense, while a bit really has just 2 values. And we're going to see that this has implication on how many operations, how many different operations one can apply on a single bit, or in a single qubit. A single bit, you can just flip it essentially. A qubit, you can rotate it in a sense. Okay, the second thing is a classical bit, a measurement of a classical bit. We don't even say a measurement. We say I read the value of a bit because reading out the value of the bit does nothing to the bit itself. In a quantum system, when you actually measure, when you want to read out the classical value of a quantum bit, you affect it, you change its state, and actually you change it in a way that in some cases is almost uncontrollable. So this is a key difference, and exploiting this type, all the properties I mentioned are part of why we get so different behavior and so different possibilities when we have quantum information systems. Another property, of course, you can copy a bit. You just look its value and you prepare another one in the same value. Quantum bits, if you don't know the quantum state to start with, you cannot copy it. This is actually something that essentially enables certain things in cryptography, this so-called quantum key distribution to quantum cryptography, because you can generate pieces of quantum information that cannot be copied. Then the final property is that if you have a string of bits, so you have multiple bits, the way to describe them is you can fully describe them in terms of the individual bits, and basically their joint system may exhibit correlations between the bits, but essentially you can describe it in a local way. Now in the qubit case, you have things that do not have a local description, so to speak. So in a sense, in some loose, philosophical sense, a quantum system behave in a holistic way in some sense. I mean, you shouldn't take me very literally on this, but they do have properties that exhibit this very peculiar property of non-locality. And of course, this is a topic of a lecture on its own, so I'm not going to get into more detail on this. So these are a number of different properties that quantum bits have from bits. And seeing those different properties, you can understand that manipulating this type of systems, manipulating systems of quantum bits, would be quite different than doing operations on classical bits. And now come to the second part, which is about the quantum speed up and those misconceptions that I mentioned. So what is a quantum computer? I mentioned what is a quantum unit of information, this qubit, but what is a quantum computer? A quantum computer is a device that you can manipulate in a programmable and fully controllable and flexible way, quantum information. So not only you want to be able to prepare a qubit, but you want to do the operations that you wish, and that you control exactly what operations you are performing, and you manipulate precisely to match the computation you want to perform. So this is the thing, and we're going to see that exactly this controllable property that is required makes quantum computers difficult. Of course, quantum bits exist in nature. I mean, you can have those photons with different polarization and so on, but what it's much harder is to actually manipulate those. And that's what makes the field challenging. Well, in practice, I mean, it makes challenging the construction of such devices. Now, as I explained, a quantum bit can be thought as a vector because it's not 0 or 1. It can be 0 or 1 and with any different so-called weight between 0 and 1. And the operation of a bit, it's a single operation that you can do to a bit, well, two. You can either leave the bit as it is, or you can flip it a single bit. And of course, you can do this conditional on the value of some other bit and so on. In the quantum bit, you can do many, many more operations. As a matter of fact, there are infinite of different operations you can do to a single qubit. And the fact that you can do different operations is what gives you this richest structure. So there are many, you can solve many problems exponentially faster, and some other not exponentially faster, as we're going to see, but faster. And the reason that this comes is because it's a different information process, so to speak. It's a different paradigm of computation, quantum computation. And of course, this opens vast possibilities in many different fields. However, having more computational power or being able to do more computations, I'm going to say exactly what I mean more, but anyway, being able to solve quicker and big number of problems brings also a threat. It's not only positive, it has a negative aspect, especially for cybersecurity. Because why and how big is this threat? Well, the concept of public key cryptography is based on having certain problems that you can verify them easily. So if you have a solution, you can check that your solution is true, but it's hard to solve them, so to speak. And this fact that it's hard to solve them without knowing some extra information is what guarantees the security of a system. And typically, I mean, the crypto systems currently used are basing this on factoring. So if you have a large number and you want to find its prime factors, this is something that is believed to be exponentially hard to do. But of course, if one gives you a factor, it's very easy to check that it factors correctly. And the assumption that this problem is hard is the basis of most of current day of the cryptography used currently, and factoring and discrete logarithm. Now, the interesting thing is that if you have a large quantum computer, you can solve both of these in polynomial time, so you can solve them efficiently. While with a classical algorithm, you would likely require super polynomial time and possibly exponential time. So, I mean, just to make what this actually means, it means that if you have a classical supercomputer, like not your laptop, your biggest supercomputer, and you try to factor a number that would take this supercomputer 1,000 years, if you have a quantum computer that has just 1,000 quantum bits, but perfect quantum bits, not the faulty ones that exist right now, it can solve it within a fraction of a second. So this really means it's a huge difference. That's what exponential separation means. So in other words, if we have such a quantum computer with 1,000 perfect qubits, everything breaks. And this includes bank transactions, state secrets, anything. And even worse, you can break things retrospectively. Why? Because I don't have a quantum computer now, but I can intercept ciphertexts, like encryptions of communication right now, and I can store them in my classical memory. And then when I have a quantum computer, I just pick them up and I decode them. So if you have a secret that you wanted to maintain secret in 20 years or 30 years, then you better not use this type of crypto systems that use factoring, because it's most likely that it would be broken then. And there are many things that we care about in the future. Well, there are state secrets, but also things like medical data and such things that you may not wish to have them leaked. So it's something that is relevant in the retrospective issue. I painted a bleak picture, but there is no need to despair. First of all, we're not there yet. You're going to see later in the talk what progress has been made, but it's far from having those 1,000 perfect qubits, first of all. And second, people are aware of these dangers and countermeasures are already developing. So it's not something that, I informed you now, and the world does know. I mean, already there's, I would say, a decade or so that people are taking seriously this prospect. Although the danger, the fact that you could factor, was known much, much earlier. It was actually known since the early 90s. However, at the time, the concept of a large quantum computer was, like almost like a science fiction. I mean, people didn't. I mean, it was just a theoretical concept. I mean, now it's no longer the case. It's something that will become realities in the future, not in the very distant future, actually. So, okay, so now it's the time to dispel a number of misconceptions, and by dispelling this misconception, you'll understand exactly what quantum computing is about, understand better the nature of the speed up, and understand better what is the issues that arise in cybersecurity and how we could possibly fix them. So the first myth is that, oh, quantum computers are much, much faster than classical computers because they can perform very quickly the operations, and much, much quicker than the classical computers. And therefore, of course, if the speed of the quantum computer is that can do the same things but faster, of course, this speed is applies to anything you're interested. That's not at all the case. Quantum computers are not faster in the speed of making operations. So if you want to make a single operation on a qubit, if anything, you can do it in slower speed than you could do it in a classical bit. The reason you get speed up, the reason you get better performance in solving problems is that quantum theory allows operations and algorithms that are not even possible to have in a classical device. And by having these different algorithms, the number of operations are fewer. The speed that you do each operation is not faster. What is faster is that you have these different operations, and these different operations allow you, if you have a good intuition and you think of a nice quantum algorithm, allow you to solve the problem with much, much fewer steps. And this is what gives you the speed up. Okay, so that's the first misconception. The second misconception, well, I helped in creating this misconception, is that quantum computers simultaneously perform all branches of a probabilistic computation, and because they span all the space of possibilities, of course, they can find solutions quickly. For example, you have a search in a database. One can imagine that you've generated a superposition that your computation spans all this database. You can immediately find the solution. This would be great, but it's not the case. So quantum computers span the space of possibilities, like the space of the different branches of a computation, in a peculiar way. They actually behave like complex probabilities, like probabilities that can take complex values. Of course, this is not, I mean, conceptually, what does a complex, actually, even a negative, what does a negative probability mean? It's not well defined, but mathematically, that's what quantum computing is about. So quantum computing, you can think of as a generalization of probability theory, where probabilities take complex values. Now, because of this thing, you have certain strange properties that your system, in some sense, fills all the space of possibilities. But at the end of the day, when you want to read out, when you want to get an outcome, you make a measurement and you just get one outcome at the end. So even if you generate a superposition of all possible branches of your computation, when you try to see what's the outcome, you're just going to get one branch. So if you just did the naive thing of generating this superposition of all branches, you're not going to get any speed up. It's just like as if you randomly picked one branch. Now, if you do some operations that you can exploit the fact that the different branches have complex weights, then you can get the speed up. And this brings us to the third misconception. So a quantum computer can give equally impressive computational speed up to all problems. You already know that this is not the case, probably. The point is that we know that you can have for certain problems like factoring, it's believed that quantum computers can give you an exponential speed up, while in other problems like an unstructured search problem, you can get just a quadratic speed up, and there are other problems with even smaller speed up or speed up in between. Now, the point is that to exploit the power of quantum computing, what you really need is you need to come up with these new algorithms that use this strangeness of quantum information in a positive way to get the speed up. And the exact speed up you get depends on your specific algorithm, or on your problem and the specific algorithm you're using. So it's very problem dependent, the speed up you get. So it's not a lot of research needs to be done on quantum algorithms, which would be a completely different field. And this is crucial also for when you want to analyze the security of a new system. You need to do also called quantum cryptanalysis. You need to make sure that you have understood the best quantum attacks for a given problem. And this is not just taking the classical algorithm. You need to use the quantum properties, so to speak. Okay, so now we go to cybersecurity. So what would be quantum safe? What would make a cryptographic classical crypto protocol secure against those quantum attacks? Well, the first intuition is we panic and we say, oh, anything that is based on computational assumptions is not going to be secure against quantum attacks, because quantum attacks give you all this extra power. So we should only turn to information theoretic security or unconditional security. This is not true, because quantum computer gives speed ups, but a quantum computer is a real device, and the real device has well-defined limitations. They're different from a classical computer, but they're well-defined. So one can base public key cryptography on quantum computational assumptions, but you need to use problems that the quantum computers cannot solve efficiently. So you cannot use factoring, but you may be able to use other problems that quantum computers do not give you exponential speed up. Examples are lattice-based problems, or finding the sorter's lattice in the sorter's vector in a lattice, and so on. And moreover, you need to do a new security analysis. You need to try to find the best algorithms for these new crypto systems in order to tune the parameters and so on, the security parameters. So you can do, but you need to be careful. You can have quantum safe computational security. Now, the final myth that I'm going to describe is that, okay, right, so in public key cryptography, I cannot use factoring, but now if I replace factoring in my cryptographic protocol with a problem that is actually hard for a quantum computer, oh, now I'm done. I'm safe. So this is something people may think, but that's also not true. So obviously, it's a necessary condition. If your problem is not hard for a quantum computer, quantum attackers will be able to break it. But it's not a sufficient condition. There is much more work to be done to ensure that a new crypto system is secure against quantum attacks. So as I described, you need to do quantum cryptanalysis in order to set the security parameters and so on. You need to have different security definitions, and even the proof techniques that are used to prove security, let's say for involved modern day cryptographic primitives like zero knowledge proofs, or a bit more involved cryptographic primitives, the techniques that are used to prove these things in the classical cryptography are not applicable for a quantum information, because quantum information has different properties. So for example, you can have a proof technique that you need to copy something. Well, you cannot copy quantum information, so you need to use a different way to prove your security. So this means, okay, we change the problem, that's the first step, but then we need to make new security definition and develop new proof techniques, well, at least for some cryptographic tasks. Okay, so I think this pretty much completes the set of myths that I wanted to explain, and how these affect cybersecurity. Okay, so all this is nice. We've been saying about these quantum computers and theoretically what speed up they can give you, and how these things would affect us. But is it something that really exists, or well, and why now, in a sense? Okay, we know quantum mechanics in the beginning of the 20th century. So what happened now? Why are we really speaking so much about these things now? After all, factoring algorithms and other of the theoretical things I'm mentioning were already known some time back. So the reason is because we're living now the dawn of a new era of quantum technology era. So there were applications of quantum theory existed from the beginning of quantum theory. and it is a theory very, very well established, and the predictions of quantum theory have been confirmed in the biggest accuracy in the history of science. So basically, only general relativity has predictions being so accurately in agreement with the predictions of quantum theory. But what happened is that those quantum systems were not controlled. So you could have some applications just by understanding how quantum systems behave, but you didn't have control. So what has changed the last decade, well, maybe even less than a decade, let's say 7 years, is that the progress that has happened in the control of quantum system is great. So now, not only we can use quantum physics for applications, now we can start speaking about processing quantum information because we have very developed control of the quantum systems. And this is the beginning of this quantum technology period that is characterized by this, by our ability to control quantum information. And this is, as I said, this is not something of a fantasy. I mean, so these are not the most updated events that I'm going to mention, but are key events. So in 2018, Google announced this quantum processor, the Bristol cone, which had 72 qubits. Now that the reason that was amazing was that this processor had 72 qubits that were fully controllable, and you could do any of the universal quantum operations required. The reason this is important, well, this sounds much less than the 1,000 qubits I mentioned before, but still, even just 72, or actually even 72 qubits, is something that you cannot classically simulate with the biggest supercomputer on our planet. So basically, even if you, there's one question whether this processor can solve something that we're interested in, but what's for sure is if you just want, with a classical supercomputer, simulate this processor and predict what this processor will give you, this is not possible. So we are in the area, we are in the time period, basically, that we can no longer simulate what this object does. Therefore, this type of processors are have the possibility of offering something that is not possible with a classical, even the most powerful supercomputer. And of course, this 72 qubit processor requires much less energy and much less space than these supercomputers. Of course, it's not as small as it looks because, well, the processor might be small, but then you need a huge fridge to freeze it to almost absolute zero because this quantum hardware architecture requires very, very low temperatures because it's based on superconductivity. But anyway, this is a different story. The point is that it's much more efficient in terms of energy. Then other things, in 2018, again, just 2 years ago, they managed to do quantum key distribution using satellites. So basically, they managed to send quantum information by satellite from Austria to China, and they managed to use this quantum information to do a secure teleconference. So you see that now quantum information not only is real, but you can send it very far and you can manipulate it. So this is something that is happening. Here is a very, well, not very actually, I think this is a 2 years old slide, so this particular one. So it's outdated. The number of countries that have invested has increased a lot, and it's indicative of the speed that the field evolves, that this is 2 years old, but the map would be quite different and the number of companies much bigger. So basically there is serious investment from governments and from big industry, and numerous quantum startups have started as well. So when I started in the field, it was a theoretical field. Now, most people, I mean, are speaking about quantum startup companies and working in the industry is no longer an academic endeavor, the quantum technology endeavor. Okay, at least in the medium scale and in the near future, or in the medium future, I'm not speaking about what will happen in 50 or 100 years, but let's say in the next 10 years, the way I imagine that the situation will be is that you will still have classical devices like small or big, I mean classical supercomputer, laptops, mobile phones, and you will also have quantum devices. You can have big universal quantum computers or small devices that generate random numbers, quantum random number generators, or other smaller devices that emit, send quantum information to other parties. So you would have all this number of classical and quantum devices, and all these classical and quantum devices will be connected in a network. Now, this network, you can have some of them being connected with classical information, some of them with quantum information. And what we really care about is how we describe the efficiency and the security of this type of hybrid communication and computation network. So this is the way I imagine that will be the future of the field. So it won't be just classical or just quantum devices, neither in the computing side nor in the communication side of things. Okay, so just a few more words now in terms of where we are and what are the near-term applications. So first of all, the known exponential speedups that I mentioned, for example, in factoring, but also other useful ones, might require of order 1,000 perfect qubits, as I mentioned. And moreover, what means perfect, it means that you need to correct the small mistakes. There is a way theoretical to do this, but in order to do this correcting of quantum bits, you need the so-called quantum error correcting codes. And now this means that you use many physical qubits, many physical imperfect qubits to create fewer perfect logical qubits, so to speak. And with current state of the art, you may need of order 1,000 classical, imperfect qubits to generate one perfect qubit. So if you want to really run source algorithm in a device with existing quality of qubits that we have now, you will need to scale it to 1 million qubits. Right. I just told you that 2 years ago, there was this big breakthrough that we had 72 qubits. Right, so that's not quite where we are. So in that sense, I told you you shouldn't worry too much. On the other hand, there is a very quick speed up in the size of the quantum devices we have, and also the theoretical developments may make it possible that you can have algorithms that you don't require so expensive quantum error correction and so on. So, okay. On the other hand, I told you that even a quantum device with few qubits cannot be classically simulated. Why? You can think that each qubit has two states and can take a value between, like superposition between these two states. And in order to keep track of what happens in a computation, if you have n qubits, you would require 2 to the n classical bits to describe this. And this means that even if you have just 50 qubits, you can no longer simulate it classically. So with 2 to the 50, that reaches pretty much the scale that you can deal in the classical supercomputers. And of course, if you go 2 to the 60, that's much above the size of that of computation that you can classically perform. And it's in the near term, like maybe in 2 or 3 years, you will have of the order of hundreds of qubits. So let's say 200, 300. Qubits will soon be available. And this is really, really far from what can be simulated. Now, the question is, this cannot be simulated, but cannot be used for those exact algorithms that I described before. But there is a big space of algorithms that could function in a different way that could give you certain applications in this intermediate scale, and these near-term applications. And this is what a lot of the research currently is interested. And there are a class of heuristic quantum algorithms that do not require quantum error correction, so that those would be very suitable for this type of near-term devices. However, those algorithms is not very clear the exact speed up that they could provide, or how they would be affected by the exact level of imperfections or noise that you have and so on. But people can plug and play. So when you have this 200 qubit device, you can use this heuristic quantum algorithm and see how it performs. And it's very likely that it will give you speed up on a number of tasks. And there are huge possibilities, and people and industry are asking these questions in many different fields, from fields like chemistry, biology, material science, physics, but also more classical things we think in computer science, like big data, optimization, machine learning, in finance. So you can have many applications, and people have been looking in all these things in parallel. And those heuristic quantum algorithms like the near-term future of the field, so to speak, because this will give us the near-term applications. Right. Okay, and that's basically finishes that part of the talk. And now I come back to cybersecurity and what quantum cybersecurity is and how we characterize the field. So what is quantum cybersecurity? It's the field that studies every impact of the development of quantum technologies on the security and privacy of communications and computations. So this has two phases, just to bring the two examples that people have heard. Of course, the one I explained already, it can have disruptive effects. So you can have the bad guys having the quantum technologies and breaking your codes. And this means that, as I mentioned, if a scalable quantum computer is built, most of the cryptography would break. The currently used cryptography would break. But then on the other hand, you can think of this as a new opportunity. Why? Because it's not only the bad guys that can have quantum technologies, it's the good guys that can also have quantum technologies. And if the honest parties in a protocol have quantum technology and they actually use it in a quantum protocol, then you can achieve things that were even impossible classically and could even make your new system secure even against those bad guys with a quantum technology. One example is the quantum key distribution that enables quantumness, enables key distribution with unconditional security, information theoretic security. Not exactly, but I mean, this is, it's a bit more subtle than that, but that's the big idea. The big idea is that you use quantum communication in order to achieve something impossible classically, which in this case actually even secures you against certain attacks that quantum computers enable. So it's like quantum information brings the problem, quantum information brings the solutions too. Anyway. Okay, right. So let's draw the field of in three broad categories. And these categories are characterized by who has quantum technologies and what quantum technologies you have. So the first level is called post-quantum security, post-quantum cryptography. And here, of course, in cryptography, you're always pessimistic. You always assume that the adversaries, the bad guys, have the full whatever power they could have. So let's imagine that they have a full-scaled quantum computer, which they don't, but let's say they do. And the honest parties, in this first case, we are pessimistic. So the honest guys are really classical. I mean, they are just using classical systems. They have no quantum ability in terms of computing or communication. So everything is classical from their side. And the adversaries have their own quantum computers. Now, in order to ensure that your system is secure in this setting, it's called post-quantum secure. And first of all, as I described, you need to have a problem, a hard problem that is hard even for those guys with a quantum computer. Then you need to modify the security definitions you have. And finally, you need to modify and find proofs that are compatible with adversaries having quantum systems and their system being described by a quantum state. So this is the first level, and this is kind of like the most urgent one. So there is competition by NIST for new standardization of cryptographic primitives that exactly takes into account this. So they ask for classical crypto systems to replace, let's say, RSA or DSA with certain other classical protocols that are post-quantum secure, and there is an active competition on this. Now, the second level is now we move a bit further and we say, okay, so the bad guys have still fully quantum abilities, but the good guys now have some quantum abilities. Okay, they don't have a quantum computer because we don't have quantum computers right now, but they do have single qubit devices that they can send and receive quantum information because this is something that is available today. So this is not something of imagination, it's something of today. And let's see, if we give these small quantum abilities to honest people, can they achieve something more? And yes, well, the answer is obviously yes, otherwise it wouldn't be in this slide of my talk. And this class, we call it quantum enhanced because your security is enhanced by having these quantum abilities. And what you could achieve certain tasks with information theoretic security, while classically was not possible, or you could achieve certain tasks with better efficiency, or you can even achieve things that were not possible classically. So, I mean, you can achieve examples of those three things. Information theoretic security is quantum key distribution. You can do things more efficiently. For example, you can have quantum fingerprintings that you require, like exponential smaller communication complexity for those protocols, or you can achieve something called position verification-based cryptography. That is something that is not even possible without quantum abilities. And finally, the third part is what we call quantum enabled. So now imagine that we live in the time that there exist quantum computers, maybe big, maybe of 100 qubits. We don't care how big, but there exist those quantum computers. And what we want is we want to have the same security guarantees that we have for classical computations. We want them to have them with these quantum computers. So for example, we know that there exist things like fully homomorphic encryption that if you want to, you can delegate your computation to the cloud in a way that the cloud doesn't learn what you are doing, or what computation, or what was your input and what is your output. So you can, there are these primitives that ensure that you can securely and with privacy access classical cloud computing. And now what we would like to have is a similar picture for quantum cloud. And as a matter of fact, this is something very crucial, because the way that quantum computers develop today is exactly in this form. So you have some central places, either companies like Google, Rigetti, IBM, that they have their own quantum computers, or big universities. And then most clients or researcher access those in a client server setting. And of course, in this case, in many cases, you would be interested in preserving the privacy of your computation, of your data, and so on. And you can imagine two different settings. So the first setting is you have this quantum computer, and the people that can access this quantum computer need to have quantum devices themselves. Okay, not quantum computers, but at least they need to send quantum information to these quantum devices. But this assumes that there exists a quantum infrastructure, and people that can access it are only the ones with quantum technology. So you won't be able to just use your phone for that. And then there is something harder, is that you can achieve the same thing, but now even from classical devices. So you can access the quantum cloud securely, even from a classical device. And this would be even more interesting to achieve. So this paints the picture of the quantum cybersecurity research. Now, before well, actually, I'm kind of running low on time, so I'm just gonna speed up a bit, because I want to say a couple of words at least for some highlight research that our group is doing, and fits exactly in this picture that I've been painting here. Well, the type of how to deal with quantum adversaries in any of those three categories has two facets. The one is the security of the specification, and the other is the security of the implementation. So as far as the specification, one way to be sure that your quantum computers are not going to break your protocol is information theoretic security. So this is a type of security that does not rely on computational assumptions. So if it doesn't rely on computational assumptions, it doesn't matter whether you have exponential computational power, because that the security is not based on this. So if you can do this, then you're fine. Of course, most tasks cannot be done with information theoretic security, unfortunately. And then the fallback option is the computational security, but at least post-quantum, that is secure against computational bounded quantum adversaries. So quantum adversaries that have polynomial size quantum, they can perform polynomial size quantum computations, which is the thing I have been talking about. Then the second thing is the issue of side channel attacks. So when you have quantum device, there are systems that are not classically so easy to understand, and they may have issues and attacks that were not foreseen for other devices. And this is the field of quantum hacking, actually, that you can do certain things, and you can break existing quantum protocols with this type of attacks. And one can either do specific countermeasures, as is done for classical devices, or you can resort to a concept called device-independent cryptography, which is something unique to quantum theory. And this non-locality I mentioned in the beginning of the lecture makes it possible. It's another very peculiar type of security that cannot be offered classically. Is some security that you can be certain about your security, even if you you have your device as a black box, and this black box is actually prepared by the adversary itself, and you can still somehow achieve securely a task by exploiting this strange property of non-locality. Okay, that's that, and I'm gonna now just state a few things that have been done and where they fit in this picture. So in our group, we've been looking on how to have a secure quantum cloud, and specifically this aspect that I told you, how to make the secure quantum cloud accessible from only classical devices. This is one field that we've been working, and we've made good progress recently. And it is theoretically possible, but of course it comes with certain cost in the quantum server, so to speak. So the quantum server needs to be large enough for this to run. So it's not something that you can use right now, but it's a potential future solution. Security of Bitcoin, which is something that is used now against the attacks of people that have quantum computers. This is in the first category, this post-quantum cryptography, because you have classical systems, classical protocol. I mean, your Bitcoin protocol is a classical protocol, and you want to ensure that this protocol remains secure when people have quantum computers. And in order to do this, you need to find the best attacks that they can do, and then make sure that you have sufficient honest computational power that can balance this, and then you need to quantify exactly what the parameters are to ensure that this is still the case in the existing network. Another notion is certified and conditional secure randomness expansion, well, essentially generating information theoretic random numbers in a way that you can certify that they're really not crypto deterministic in a sense. And this is another thing that, I mean, this would lie in the second category of quantum enabled, because to do this, you need some small quantum technology, quantum device, but not a quantum computing device. And this is again is enabled by this concept of non-locality. And finally, quantum digital signatures, again, that you can achieve digital signatures, well, some type of digital signature with unconditional security. Again, if you have this type of, if you can exchange simple qubits between parties, so to speak. So if you have parties that have these small quantum devices, so these two lie in the second class of the categories I painted. This is in the first, and this is in the third. So that's how the recent research of our group fits in this picture, in the landscape of the quantum cybersecurity I described. Right. So, well, thanks for your attention, and I'll stop now, so we can have some time for questions.
Thank you so much, Petros. That was a fantastic talk, and I know I certainly believed in a lot of those myths, so it was great to see them dispelled. So we actually have a number of questions in the chat, so we'll just get started. The first question is, what is your typical day as a scientist, as a researcher like?
Well, now or before the COVID? Okay, right. I understand the question. It was just a joke. Right. So, I mean, researchers do very different things. Personally, I'm a theoretician. So, I mean, the research part of most of my research is basically trying to prove in this field at least, and because I'm working on other things in quantum computing. So my research is mostly about developing those protocols, improving the security of those protocols in mathematical terms. But of course, there are many different aspects of each of these. So I mean, it really varies a lot, and on the topic one researches. So if the question is in terms of career, I mean, what an academic in the field is doing. I mean, an academic in the field, of course, has many different things, from teaching, getting grants, and doing research, so importantly. And when doing research, you start manage a research group in a sense. So you need to separate things. So my research itself is theoretical, but we talk to experimentalists. So we are very well linked with labs that actually have quantum computers and have quantum communication systems. And also there is the computational aspect, like coding and so on, or making better implementations. But my core research as a researcher is on constructing the protocols and proving their security. I hope that answers a bit the question and is not off the point of the question.
Yeah, good answer. The second question is, what kind of advice would you give to yourself as an undergrad who was perhaps thinking of a career in academia? If you could go back in time, give yourself any piece of advice, what would it be?
I'm not sure I'm the best person to ask, because I was, I wanted to go to academia, and actually my field became much more, hyped and trendy from when I started. So I really started in the field from pure curiosity and from my desire to understand things better. Of course, it's very exciting when you see that the things that you dreamt there is something that actually happens. So that's an exciting time to be. But yeah, I don't know. I mean, the question is, what advice would they give? What things one should be careful when pursuing an academic career, or how would they encourage a person to turn to academia? I mean, if it's the first, I would say that one needs to keep options open. So you need to you need to see the whole field, so to speak. So you need to broaden your view and have research experience before you commit too much, because research is not for everybody. I mean, I believe everyone can do everything, but it's not in the taste of everyone. I mean, it may sound different than what it is when you actually do it. And also in academia, one needs to take into account that it's a research career, but it's not only a research career, it's also a teaching career, which is something that you also need to be very, it should be something that you like to do. I mean, well, of course, there exist paths in academia that are only research only, but there are much fewer. Yeah, I don't know if that's what I would say.
Yeah, okay. The next thing is actually a comment. No, it's not a question. Don't really know what it means. It just says the Schrodinger's bit. I don't know if you want to say anything about that.
The Schrodinger's what?
The Schrodinger's bit.
Right. Yeah. Well, yes. Sure. Yeah. So that's the Schrödinger cat. That's the point. Yes. So it's that's. I mean, Schrödinger cat is. Yeah. Okay. It's the same, and the concept of superposition is the same thing, but for qubits. Yeah.
Right. So the next question is, how is it physically possible to measure the state of a qubit? How can qubits be preserved in the needed state if they change state after they're being measured? How can you store data in it? What happens if you try to read it?
Right. Yes. So that's the point. So measurement happens at the end of the computation. So during the computation, you don't measure, because if you measure, you will disturb it. Depending on what type of measurement, you may completely destroy the information or not. But if you actually completely or partially, but you change the state. So really, when you measure a system, it's no longer, I mean, you no longer store it in a sense. So what you need to do, you need to do all the computation, and now at the end, the output quantum state encodes the useful information, and now you make a measurement, and then you reset your computation. You reset those qubits more or less, I mean, usually. And now what is hard is to store the quantum information in the middle. So when you do some operations in these qubits and these qubits wait, or you want to make some operations in these qubits and then a second operation on this is something hard. Even if you don't measure them yourself, it's very hard to keep coherent. So it's very hard to ensure that random measurements or decoherence from the environment doesn't happen with quantum systems. And that's one of the big challenges to building bigger quantum computers. Exactly, the fact that you cannot keep the quantum state untouched, even if you yourself don't measure it, because it interacts with the environment. That's why, for example, you need to be really cooled down some of those superconducting quantum computers, for example.
Right, thank you. The next question is, do you see mainstream quantum, it's a two-part question, so do you see quantum computing becoming mainstream for consumers, or will it remain a tool for research and corporate groups? And the second part is, if so, what do you think the event horizon on commercially available quantum computers for consumers is?
Okay, well, depends what consumers you mean. I mean, so first of all, I think that quantum computers will become the standard. So if you ask me in the future, I mean, 30 years, whatever from now, I believe that eventually you wouldn't have computer science departments, you will have quantum computer science departments, I believe, in the future. Of course, we're not in this level. That's why I described that you will have classical and quantum devices in any medium future, and immediate, of course. Now, there are already consumers, clients that, not researcher, I mean, like companies that are doing everyday things from finance to medicine to whatever, that they contact quantum researchers. Of course, at the point that quantum computers will, and right now there are quantum computers, small, not the ones that give you speed up yet, but that you could access from your computer. So you can go on your computer and access the quantum computer of IBM right now and run a small quantum computation. Of course, when it becomes, when you will have in the quantum cloud bigger quantum computers, they will obviously charge you. For now, some of these are completely free, because they're like toy quantum computers right now. And so this is not at all far. So I would say, I don't know, in 5 to 10 years, you will have a lot of companies, and well, maybe not every single person accessing a quantum computer, but you will have access. And the more the field develops, the more the user friendliness it becomes important, because of course you won't have people writing quantum algorithms, but you would have people wanting to use them. So you would need to have an interface that they basically state the problem and it compiles and it gives you kind of the answer without you needing to know how quantum bits behave. After all, right now you don't know how your classical computer works. You just write a command in a very high level language. I mean, and then that's translated to. So in a sense, the quantum algorithms I've been speaking of is almost like writing them to, like machine language, and that of course will change when the more these computers will become available. So I believe in 5, 10 years you will have, already you have those quantum computers being accessible. So at the smaller ones, but I believe in 5 years you will have ones that can provide speed up that will be accessible from general people. Yeah, I mean, this doesn't mean that those will solve all your problems. I mean, they may give you speed up specific problems, and that's a different story, but it's not something only for researcher, for sure.
Yeah, that actually ties in nicely to the next question, which is, are there any differences in writing code for a quantum computer, especially in low-level coding? Like, what is the process of compilation and assembling in quantum computing?
Well, I mean, there isn't. I mean, there exist different. I mean, different languages. So for now, you would write things like. I mean, the ones I know, you would basically write a quantum circuit in a sense. So you do need to understand some quantum, but they do exist. And they are being developing now higher level languages. So right now, I mean, you need to know the operations. So it's like, I mean, like if you wrote a classical program and you need to write the NOT and AND gates, but you would need to do this with quantum gates and quantum bits, so to speak. I mean, but so this is the level of languages that myself in research I would find useful. But of course, this is something I don't follow, because every month there is an announcement that something more is developed. So it's something that will be, I mean, higher level languages are being developed, so to speak.
Right. How much time do we have we have a few more questions. How much time do we have?
Well, we can have maybe 2 to 3 minutes. So.
Okay. So if qubits can have a range of different states, can that very property be used for encryption?
Right. Not exactly, not directly, because the point is that you can have all this, but when you read out, you get one. So if you have a quantum bit, you can have infinite. A single qubit can be in one of infinite states. But when you make a measurement, you'll get a single bit outcome. So in a sense, this is not really accessible. It's not really that you have both states with this continuous value. It's just it behaves strangely. It's a good way to mathematically describe it as being both 0 and 1, and basically being a vector in a vector space. But it's not something that you can exploit itself, because when you measure, you need classical bits of information to take out, and this there's a bound of how much classical information you can encode on a single qubit. Yeah, so that's the answer to that.
Right. Final question, I guess, for the day is, I know there's going to be a lot of people from EUYSRA watching this who want to do their own informatics research project or physics research project, and maybe they want to do something with quantum computing. Is there a way for them to do any quantum computing projects?
Well, well, if they're students in informatics, there are projects. Well, first of all, actually, the School of Informatics has a quite big quantum informatics group. So there's five staff members and some, I don't know, 15 postdocs and some 15 PhD students. So it's quite a big group. And every year there are certain projects proposed by us that are quantum. And of course, if someone, well, I would say that the first thing would be to take one of the quantum courses right now, the quantum computing course, or contact the people in the quantum informatics group and discuss the possibility. I mean, usually you would take one of the proposed projects, but if you have some very concrete project, you could approach any of the people in the quantum informatics group. There is a paid quantum informatics group. If you search Edinburgh, you can find the members and so on, contacts.
Okay, great. I think that brings us to the end of our time, because I know you're a very busy guy. You need to work on preventing the bad guys from breaking all the encryption. So thank you so much for coming, Petros. On behalf of EUYSRA, we'd like to thank you once again. And also, we have a brainstorming session coming up on Thursday from 6 to 7 p.m. where if you're interested in doing a research project, maybe with quantum computing and informatics and math, or maybe about biology or chemistry or physics or something else, you can come along to this event and you can brainstorm your own events. So I'm just going to put the link to that down in the description. But of course, take a look at the EUYSRA Facebook page as well for more details. Petros, any closing thoughts that you might have?
No, well, thank you for inviting me, and I hope that this was a useful experience for the participants.
It was our pleasure. Very informative, and the recording will stay available. So if you want to rewatch it or share it with your friends, you can do so.